In this video, I'm going to be working out a common fluid problem where we're trying to figure out the volume of balloon that's filled with helium that you would need to carry an 80 kilogram woman. So with our fluid problems, a lot of them will involve liquids. This one in particular is focused on gases. So let's go ahead and draw out what we have here. We have a large balloon that's filled with helium, and then it is carrying an 80 kilogram woman, and we'll say that that basket is included with that 80 kilogram mass. So we have a few different things going on. We have the air molecules completely surrounding the helium balloon, and then we also have the helium inside of the balloon itself. So if we take a look at this whole system of the 80 kilogram woman and the basket together with the balloon, assuming that it's massless, and then the helium in the inside, we can go ahead and draw all the forces that are going on. So we have the force of gravity for the woman. I'll put a W. We have an Fg for the helium, and then we also have that upward buoyant force from the air. So we have three forces that we're going to be dealing with. We have our buoyant force equal to our Fg of the woman and Fg of the helium together. Now what we can do is, if we have some forces, we can either put them in the form of mg, or we could put them in the form of rho vg. So for our force, buoyant force of the air over here, we're definitely going to want to put that into the rho vg form. For the woman, we're going to want to put this in the mg form. And then for the helium, we're going to do rho vg, because we know the gas and we know the density of each of these forces that we broke into the rho vg. Now our g's are going to drop out, which is nice. And then let's go ahead and plug some stuff in and see if we can solve for what we're looking for. So we have the rho of air, which is 1.29 kilograms per meter cubed. We do not have the volume. That is equal to the mass of the woman plus rho of the helium, 0.164, helium being a gas with a pretty low density, times the V over here. Now, these V's, though, happen to be the same, because the amount of helium that we have inside the balloon causes that same amount of air to be displaced. So these V's are actually going to be the same unknown variable. So we can go ahead and subtract 0.164 V from both sides. And then we can go ahead and finish that off with one more step. And then we have a final volume of 71.03 meters cubed. So that is the volume of our helium inside the balloon, which also equals the amount of volume for the air that is displaced for this V over here. So when you're setting up a problem like this, or any similar type problem, you want to consider the mass or the container. All of that together will have a certain Fg. And then we have the Fg of the gas itself. And then we have the buoyant force counteracting in a lot of these cases where you're displacing air or water. Obviously, kind of depends on the situation. And then you use either an mg or a rho vg. Typically, if it's a certain physical solid mass, you're going to use mg. And then if it's some kind of liquid or gas, then you typically use rho VG for that. And then a lot of times you might have a G that cancels out, do a little bit of algebra, and then you're able to solve for the volume. So I hope that was helpful to you. Thank you for watching and listening.